In this video, I'm going to talk about flowing fluid into a tank at constant temperature with no chemical reaction. Nothing interesting, in fact. So let me draw what I mean. So I have a stirred tank, and I just flow something into it, some fluid. Let's assume it has constant density. The height of my tank is L. I have a constant cross-sectional area, A sub C, and we have an F out. I'm going to call this L0 just to make sure it's clear. That's the initial height of fluid in the tank. And just to keep it simple, we're going to assume constant density and that there's really no heat transfer, no chemical reaction, no change in composition, just fluid flowing into a tank. And what I want to solve for, we're not solving actually right now. What I want to do is formulate a differential equation for L as a function of time, right? The liquid level as a function of time. So in order to do that, I'm going to draw my control volume. I don't often do this for a stirred tank because it's usually just the tank. And I'm going to look at the mass. I'm going to do a balance on the overall mass. So at any given time, the mass is actually the mass of fluid inside the tank is going to be the density times the volume of fluid in the tank. So the volume is V equals LAC. The mass in the tank is going to equal rho V, right? Rho is mass per unit volume. V is going to be the volume in the tank, which is also rho LAC. Remember that rho and AC are constant. The level can go up and down, but we're assuming that, say, this is a cylindrical tank, its cross-section doesn't change. And the density of the fluid doesn't change because there's no change in things like temperature or composition. So let's do a material balance. It may be tempting to balance volume, fluid volume, which would actually be correct if density is constant, but strictly speaking, we should do a mass balance. Meaning that mass is neither created nor destroyed. If density changes, then volume, strictly speaking, is not conserved. Okay, so I'm going to say input minus output plus generation minus consumption equals accumulation. So, and I'm also looking over a interval of time delta t. So what I'm going to do is I'm going to say the accumulation is V at t plus delta t and minus V at t. Now this is also equal to, rho V, that's mass. This would actually be rho AC times the quantity L at t plus delta t minus L at t, right? Because rho and AC are constant, they can be factored out. So what goes in along that delta t, or during the duration delta t? Well, F in is going to be a flow rate. It usually have the units of volume per time. So to get the units right, we need to multiply by the density, that's mass per time. And now if we multiply by delta t, we get mass to match the units on the other side. The output is going to be rho F out delta t. Mass in this system is neither created nor destroyed. So generation is 0, consumption is 0. And so the density cancels on both sides. And so what we get here is L at t plus delta t minus L at t divided by delta t is equal to F in minus F out over A sub c. And if I take the limit as delta t goes to 0, then I get this becomes dl dt equals F in minus F out over AC. So this was our purpose to derive this equation. This is a differential equation that would allow me to calculate L as a function of time if I knew these quantities, F in, F out. By the way, I don't know if I stated this explicitly, but I've been assuming that F in and F out are constant. And I think it should be a fairly intuitive result, because if the flow rate in is higher than the flow rate out, then water should accumulate in the tank and the liquid level should go up. However, if the opposite is true, if I'm putting less in than I'm drawing out, then dl dt ought to be negative and the fluid should drain from the tank. We're not really going to focus right now on solving differential equations, although this one has a pretty simple solution. It's just linear in time. L would be linear in time. But I want to focus on setting up differential equations.